Glad you know. The next topic is the calculation of moment of inertia of a solid sphere. So we have already covered the derivation of the moment of inertia of a rod, then a ring, then disk, then sphere also. We have seen, and we have seen the moment of inertia of these objects taking different axes. So today we will have the derivation of the moment of inertia of a solid sphere. The axis that we are taking for this first is about a diameter. So we have a solid sphere here, which I have drawn here. The center of the sphere is O. The radius of the sphere is capital R. And the mass of this sphere is taken to be capital M. So as we have done earlier, so we will consider how this is made up of. So what is actually a solid sphere consisting of? So we can say that a solid sphere is consisting of, if you imagine that uh, the section with which this solid sphere is made of is a disk. Okay, so here I have a disk here. So it is just like this. ഇതൊരു സോളിഡ് സ്ഫിയർ ആണ്. അപ്പോൾ ഇത് മേഡപ്പ് ഇതിനെ മേക്ക് ചെയ്തിരിക്കുന്നത് കുറെ ഡിസ്കുകൾ ചേർന്നിട്ടാണ്. സോ ദിസ് സോളിഡ് സ്ഫിയർ ഈസ് മേഡ് അപ്പ് ഓഫ് എ ലാർജ് നമ്പർ ഓഫ് ഡിസ്ക്. ഫോർ എക്സാമ്പിൾ, ഇഫ് ഐ cut this, I will have a disk here, here, here. So like that. So this is, so I have a, this disk is of a larger radius. പക്ഷേ ഇത് ഇങ്ങനെ ഒരു ഡിസ്ക് ഉണ്ടാവും. Another disk I have, another disk I have, another disk I have. So I can imagine that this solid sphere is made up of a large number of disks. Okay, so such a disk I have drawn here. Such a slice is actually a slice. If I am slicing like this, so I have a slice here which is PQ of width dx. Okay, width dx, which is at a distance x from the center of the solid sphere. So this is what we are considering. അപ്പോൾ നമ്മൾ ആദ്യം ചെയ്യാൻ പോകുന്നത് വെച്ചാൽ, as we have done earlier, we will find the mass of this strip. Then you find the moment of inertia of this strip about this axis. So it is about this axis, about this diameter AB, that we are going to determine the moment of inertia. So it is like this. If I have an axis passing through, this is a suppose this is a solid sphere. This is actually a hollow sphere. Supposing that this is a solid sphere, I have an axis passing through the diameter like this. So it will get inserted here, go through the inside and come at this point outwards. Okay, so I can say that this solid is made up of a large number of disks. One disk is like this. It's not actually a disk, but you can consider that this is a slice. If I am slicing this further, I will have one slice here, one slice here, another slice here, like that. All those slices will make this solid sphere. So it is just to explain more, I can draw a picture like this. I have when I am slicing this solid sphere, I may be getting like this. One portion it will look like this. Another portion will look like this. Okay, increasing radius. Another disk will be like this. Like this. The next one will be like this. Okay, like this. And finally, we'll have a portion like this. So when all these things are joined, I will get a sphere. Okay, so just joining like this. So this portion will be like this. Okay, so when they are joined, so I can imagine that a solid sphere is made up of discs. So I am considering such a disk PQ. So what are the measurements of this disk? It is at a distance x from the center. Also we can say that the radius of this disk is y. Okay, here we have x, then y. Here we have r, which is the radius of the solid sphere. So it will be, when I am taking it out, it will be looking like this. This is a disk. Okay, and the radius of this disk will be what? It will be y. So it is about this axis that we are going to find out the moment of inertia of this disk. Okay, actually this is a disk. Okay, so we have already found out this to be mr squared by 2. So we will come to that during the derivation. Okay, anyway, I am considering this disk. Now we are going to the derivation. The first step, as always, is to determine either you will determine mass per unit length in the case of bar, or mass per unit area, or mass per unit volume. So in the case of uniform rod, we were taking mass per unit length. In the case of ring, we were taking mass per unit area. Here what we are taking is mass per unit volume of the sphere. So the first step is mass per unit volume of the sphere. So what is the mass? Mass is m, radius is r. You know that the volume of this sphere is 4 by 3 pi r cube. So I can write mass per unit volume as m by 4 by 3 pi r cube. Okay, this I can take as, this can be designated as rho. Okay, rho is equal, and this rho will be obtained as 3 goes to the numerator, then 3m by 4 pi r. So this is a mass per unit length. So now I mean mass per unit volume I have got. Now the slice we will take. So this volume of the slice we will take. Then we will multiply mass per unit volume of the sphere into that particular volume. So what is the volume of this sphere? So volume of this slice, volume of this small slice, volume of slice PQ. In order to find that, we will have to find the area into thickness. So that is the volume. So volume of slice PQ will be equal to area of a slice PQ into thickness. Okay. So what is area? So area, this is a disk of radius y. So if the radius area is given by pi y squared. Okay. Y squared into thickness. Okay. But this y squared is nothing but r squared minus x squared. So according to this, pi over x squared plus y squared will give you r squared. So this y squared will be r squared minus x squared dx. So this is the volume of the slice PQ. So that is area of the slice PQ is pi y squared dx, because it is a disk, pi r squared into thickness. Y squared is r squared minus x squared into dx. So this is the volume of slice PQ. This is a mass per unit volume. So therefore, mass of the slice PQ is given by, what is that? This is mass per unit volume. This is the volume of this particular slice. So I can write 3m by 4 pi r cube into the corresponding volume, that is pi into r squared minus x squared into dx. Okay. So pi and pi get cancelled. This will be 3m by 4r cube into 3m by 4r cube into r squared minus x squared dx. So this is what we are getting. So now we have got the mass of the slice PQ. And what is the next step? Next step is to find out the moment of inertia of this slice about this axis. Okay. This is a disk. What is the moment of inertia of a disk passing about an axis passing through the center perpendicular to its plane? So this slice, if you are taking this, this is actually a disk. Okay. And now we have got the mass of this disk. Now we have the axis like this, AB. Now we have already found out we have already derived the expression for the moment of inertia of this disk about this diameter, that is about an axis which is passing through the center perpendicular to its plane. That is nothing but mr squared by 2. mr squared by 2. Mass of this slice we have found out as this one, that into r squared by 2 will give you the moment of inertia of this disk about this axis. Now what is the next step? After finding out the moment of inertia of this slice about this diameter, we can argue that such slices will come from here to here. this sphere is made up of such slices which are lying between this point A and this point B. Okay, if that is an axis, this is a point A and this is a point B, then I can say that this such disks are lying between this point and this point. What is this point? This point will take us 0. Just like we did in the case of a uniform bar, I will take this point as 0. Then going to the left, this point will be, and then either this is minus r. Okay, because this is the radius. This is 2r. Total diameter is 2 into r, where r is the radius. This point is, if I am taking as 0, this point is minus r. Going to the number line, left leg it is minus r. Here 0 plus r. Okay, so this point is corresponding to minus r. Then this is corresponding to 0. Then this is corresponding to plus r. So I can argue that this solid sphere is consisting of such disks extending from minus r to plus r. So we can integrate. After getting the moment of inertia of this disk about this axis, I can integrate whatever I am getting, that expression within limits, I mean from limit minus r to plus r. Then I will get the moment of inertia of the solid sphere about this diameter. Okay, that is our procedure. Now after getting the mass of the slice, we are going to mi of this slice. Mi of the slice means it is a disk. Okay, it is slice as well as disk. Okay, about PQ is equal to. So this is the same problem we have discussed earlier. So this is a disk. AB is the axis passing. Here y is the radius. So what is mi of the disk about PQ? That we have already derived as m r squared by 2. That is mass of the disk into radius squared divided by 2. So mass of the slice into its radius and the square divided by 2i. So what is mass? Mass is here, radius is y, and there is 2. So I can write mass into, that is equal to 3m by 4r cube r squared minus x squared dx. So mass is written, then radius squared, that is y squared, because y is the radius of this disk, divided by 2. So that will give you the moment of inertia of the disk. This is this disk about this axis. Then the next step is to integrate from minus r to plus r, because such disk can exist between minus r to plus r. Okay. So rewriting the equation here, mi of the disk PQ about AB is equal to 3m by 8r cube into r squared minus x squared dx. So as I already said, this sphere can be made considered to be made up of such disk with x varying from minus r to plus r. So the mi of this sphere can be obtained by integration. That is mi of, therefore mi of the sphere about AB is obtained by, so I can take this to be I. Okay, or I can write here AB is given by I is equal to minus I is equal to minus R to plus R of this one, that is 3m by 8r cube r squared minus x squared the whole squared dx. Now we will expand this one, r squared minus x squared the whole squared dx, and then all that. You take the constant outside the integral. So how will you do that? 3m by 8r cube. So here I have minus r to plus r. So we have the limit from minus r to plus r. This can be written as 0 to r. For simplicity, I can write 0 to r. When I am writing 0 to r, I have to put 1, 2 here. Okay. When I am putting 2 here, there will be 4 coming here. Okay. That I can write here. That is 2 into 0 to r 3m by 8r cube. Okay. I can take it out also. So that is 2 into I can take this out. That is 3m by 8r cube. I take out, then integral, then it will become 0 to r. Okay, 0 to r, then r squared minus x squared the whole square dx. So this is what we are getting. Now 2 and 8 cancel. Here we will have 4. That is 3m by 4r cube. Then integral 0 to r. Expand this one. We will get a minus b the whole square. We will get r raised to 4 s squared minus 2ab plus b squared. So r raised to 4 minus 2r squared x squared plus x raised to 4 dx. So this is what we are getting. Now we have to expand this one and write here. Okay. So now integrating this, we will have 3m by 4r cube, then 0 to r, then you will integrate this. So what will be the result? I will write here I is equal to 3m by 4r cube, then integrating this is r raised to 4 dx. Okay, r raised to 4 dx, remember it will be r raised to 4 x. Okay, now 2r squared x squared dx minus 2r squared x squared dx. So that will be, when integrated, it will become, what is the integral? X squared dx will become x cube by 3. Okay, x squared dx integrated plus x raised to 4. X raised to 4 when integrated, it becomes x raised to 5 by 5. Okay, because the integral of x raised to n is x raised to n plus 1 by n plus 1. Okay, what is the limit? 0 to r. Okay, so in apply limit, when applying r, you will get an equation minus, when you apply 0, this will become 0, x is equal to 0, this time becomes 0, x is equal to 0, second time becomes 0, x is equal to 0, this time becomes 0, all the terms become 0. So you have to apply only the top limit, upper limit. So what will you get? This can be written as 3m by 4r cube, applying the upper limit, then r raised to 4 into r, x in the sign of r, instead of x you put r, minus 2r squared, instead of x apply r, that is r cube plus r raised to 5 by 5. This is what we are going to get. Now this can be written as 3m by 4r cube, r raised to 5 minus 2r raised to 5 plus r raised to 5 by 5. Okay, 2r squared x cube by 3. So that is r cube by 3. 3 is also r by 3. Okay, this is what we are going to get. Okay, now this is 3 into 5, 15 LCM that we can take here. 3m by 4r cube. Now here I can write 15. Now this is 15. This should be 15. 15 r raised to 5 minus, this is 15 here, so it should be multiplied by 5. So minus 10 r raised to 5 plus, this should be multiplied by 3 to get this one. So plus 3 r raised to 5. This is what we are going to add. So we have 15 r raised to 5, 10, 3. So what is this? This will be 15 plus 3, that is 18 minus 10. It will be 8 r raised to 5 by 5. So I can write here 3m by 4r cube. Okay, 3m by 4r cube. Here we'll have 8 r raised to 5 by 50. What it will be? This will cut. Okay, 5 will be coming here. Here it will be 2. So I can write 3, 5, then 2 here. So what is this? 2, 5 here. Then r cube. Then here it will be r squared. Now I can write it is I is equal to 2 by 5. Okay, 2 by 5 mr squared. This is what we are going to get. So moment of inertia of a sphere about an axis passing through its center, like this, about a diameter. So when I am inserting like this, the ball will be rotating like this. So if that is the axis about which this ball is rotating, it will be rotating like this. will be getting inserted in through the insert. It will go and come through the other side. So if that is the case, the moment of inertia of this sphere about this diameter AB is given by I is equal to 2 by 5 m r squared, where m is the mass of the sphere, r is the radius of the sphere. So this is the required moment of inertia. Okay. Now we have already found out the moment of inertia of this sphere about a diameter. Now we are taking another axis, which is the tangent. What is tangent? So I have already have a sphere like this. Okay. Now we have found out this about this diameter. We have already taken this AB. About this AB, we have already derived it to be this moment of inertia of this sphere about this axis of the diameter is 2 by 5 m r squared. That we have already derived. Now consider another axis, which is a tangent. Tangent will be passing through this point. So this is a tangent that we are considering like this. Okay. I am taking this axis to be CD. Okay, CD. So if we know this, how will you find out moment of inertia of the sphere about another axis, which is a tangent? So for this we apply nothing but the parallel axis theorem. What is parallel axis theorem? Parallel axis theorem states that if you have two parallel axes, one is passing through the center of mass, the other one is given by this plus the product of mass and the square of the distance between the axis. So square distance between this axis and this axis, it is clear from this figure that it is r itself, radius of the sphere itself. So what you have to do, applying parallel axis theorem, applying parallel axis theorem, this can be taken to be I. Okay, this can be taken to be for this case I can take this to be I0. Okay, this is what we want to find out. When I is equal to I0 plus m into the distance between a squared, that is r squared. Okay, so sum of moment of inertia about an axis passing through the center of mass plus product of mass and square of the distance between the two parallel axes. That is what we are going to do. So now I0 is 2 by 5 mr squared plus mr squared. What is 2 by 5 mr squared plus mr squared? It is mr squared into 2 by so mr squared 2 by 5 plus 1. It is 7 by 5. So this will be I is equal to 7 by 5 mr squared. Okay, 7 by 5. So I can write this as 7 by 5 mr. So what is the meaning? If I have a solid sphere, if I have an axis passing through the center, do like this. This one is, as you look from here, you can feel that this is passing through the center. The moment of inertia is 2 by 5 mr squared. If I am taking another axis here, passing through the tangent, it will be 7 by 5 mr squared. 7 by 5 mr squared, 2 by 5 mr squared, passing through the center. Okay. Thank you.